Welcome to this course on cathodic protection engineering. So far we have seen that the cathodic protection engineering involves two basic concepts. First, the electrochemical corrosion, and second, the reticle engineering. When we talk about maintaining the potential of its structures with respect to the soil and the relation between that potential and the current, the electrochemistry is involved. However, the current that flows in the soil and as well as in the structure are governed by the reticle engineering concepts. These we have seen mostly as applicable to the pipeline structures. The governing resistance of the anode ground bed, the criteria for cathodic protection, and even the various forms of corrosion the buried structures face in the soil, we all seen earlier in detail. Today in lecture we will be talking about the cathodic protection of tanks, offshore structures and the ships. If you look at that, the major principles as applied to the pipelines are very similar. And so, we are not going to talk about in detail all the electrochemical corrosion concepts or the calculation of resistivity of the anodes in the soil. All this we are not going to discuss today. What we will be discussing today will be very specific aspects as applicable to tanks, offshore structures and ships. In today's lecture, we would have the following content. We will start with discussing the cathodic protection of tanks and tank bottoms, and then we will move on to the heat exchangers, very small discussion on the heat exchangers, and then we will discuss again in briefly the offshore structures that involve pipelines, piling, jetties and floating structures. So, let us start our discussion straight into the tanks. The storage tanks, if you look at it, next only comes to the pipelines in terms of the extent of cathodic protection applied to the structures. So, let us look at now the cathodic protection of storage tanks. The storage tanks are classified into two categories: above ground storage tanks and those which lie underground. These two storage tanks governed by two kind of NIST standards, which is RP 0193 and the RP 0285 for the underground storage tanks. The nitty-gritty details of the cathodic protection as applicable to these tanks can be seen in these standards. What we will be looking at here is the general principles, the concepts behind the cathodic protection of these two types of storage tanks. At the outset, we need to distinguish between what makes the underground tank different from the above ground tank in terms of the definition. Those tanks which are buried at least about 10% of its combined volume in the underground is called as the underground storage tanks. Let us look at the generalities that are involved in the storage tanks. The storage tanks mostly are buried in the soil, be it above ground storage tanks or underground storage tanks. They are exposed to the soils mostly, and so whatever we discussed in relation to the pipelines which are buried in the soil in terms of the forms of corrosion that you see here, like what types of corrosion, like the bacterial corrosion, the differential aeration corrosion, all these are applicable to the storage tanks as well. The cathodic protection criteria as applicable to the pipelines are as well applicable to the storage tanks. The surveys in relation to soil resistivity, pipe to soil, the current requirement, even the stray current corrosion are all applicable to the storage tanks. The anode selection criteria, the way you calculate the ground resistance is very much similar to the way you do it for the pipelines. The storage tanks are also suffering from stray current corrosion because there are current that strays from the anodes of the cathodic protection systems to other structures and then return back to the storage tanks. So, they also suffer stray current corrosion. So, these are generalities which we will not be discussing in this lecture. Let us look at the specific issues that are applicable or one should be worried about when you talk about the storage tanks. The storage tanks, we know there are certain process liquids which are being stored or been taken out. So, there are inlets and outlet pipelines, and these pipelines required to be electrically isolated, or if you cannot isolate them, we need to look at as a composite structure when you design the cathodic protection systems. When you have again the tanks would have the mechanical joints, and it is necessary that one ensures that these mechanical joints are electrically continuous, so that the current will flow into the structures. The storage tanks are earthed using copper, but whenever you go for cathodic protection systems, they are replaced with the galvanic anodes or the galvanized steels. There are special issues associated with the above ground storage tanks, especially because when you empty this tank, the contact between the soil and the tank bottom is getting loosened, and thereby it is hard to measure the tank to the soil potentials. So, the tank to soil potentials, we generally call also as pipe to soil potential, is one measured only when the tank is completely filled up. There is one more issue that is problematic to the tanks, that is how to measure the structure to soil potentials, okay, especially the inaccessible areas. You would notice that there are tanks which are of very large diameters, of few meter diameter the tanks, in which case the reference electrodes cannot be accessed the bottom of the tanks. So, the measuring potentials of the structure towards the center of the bottom of the tank is always a difficult issue. Okay. So, in order to do this, what is done is people use perforated plastic conduits through which the reference electrodes are passed across the bottom of the tank to measure the potentials. It is also possible to use zinc electrodes, because the zinc electrodes is just buried in the soil. The normal reference electrodes like copper sulfate or silver chloride, these reference electrodes, they have the solutions, they dry up over a time period. So, these electrodes they become damaged, they do not show the values, and so there is a need to change these reference electrodes with respect to time, which is not possible in the case of the tank bottoms. So, in order to do this, the zinc electrodes can be used, because zinc electrodes are buried in the soil. The only condition is that zinc should not be passivated. The zinc sometimes get passivated if you have carbonates in the soil. The other issue that is specific to tank is during the commissioning of the tank, and one should avoid welding at the center of the bottom of the tank, but that is easier said than done. When you are welding them, then the coating get damaged, then the current requirement to protect the tank at that location becomes very high. Similar to the pipelines, the current requirements for the storage tanks to protect cathodically can be either measured or calculated. Generally, the current requirement for protecting the storage tanks lies in the range of 10 to 20 milliampere per meter square for bare tanks. For the coated tanks, the current can be significantly reduced to 100 to 10 microamperes per meter square. It is also possible, we have seen that measuring the potential of the tank with respect to soil is very intricate. Especially at the center of the tank, it is very difficult to measure the potential of the tank with respect to soil, because the reference electrode cannot be accessed. The only way it can be done, as we have seen before, is by using the perforated plastic conduits through which the reference electrodes are sent. However, it is also possible to estimate the potential of the structure with respect to soil at the center of a cathodically protected tanks, and that is done by using a simple equation, that is Ohm's law. Let me just take this pointer here. So, the calculation of the potential at a given location is based on simple Ohm's law, E equal to IR, and we can get this E value provided that you can be able to calculate the current that is required for protecting the structure and the resistance offered by the soil between the two locations, right. Now, we have seen earlier that the current density required for protecting the structures can be either calculated, can be measured. So, that means the current density required for cathodic protection is known, the soil resistivity is known, and we also assume that the soil is of uniform chemistry nature, and so the soil resistivity across the bottom of the tank is quite uniform. In fact, when we lay down or when we commission the tanks, we normally spread the high resistivity soil such as the sand here. We see below how one can calculate the potential of the tank at its center with respect to soil. First is to calculate the current required for cathode protection. That is done by knowing the current density and then knowing the area of the tank. So, you know the total current required for the protecting the tank can be calculated. The next step is to calculate the potential drop across the tank, right. The potential drop across the tank, delta E, is given by the potential drop can be calculated based on this equation, which is pi r square, which represents the total current, and the rho delta r upon 2 pi r square. If you solve this equation, it becomes delta E upon rho into delta r by 2. Okay. If one integrates this potential drop with respect to the distance, okay, and you get here which is the radius of the tank, then E turns out to be rho into current density into radius of the tank upon 2 here. So, it is possible to calculate the potential of the tank at the center if you know the potential of the tank at the edge. An example is given below. To illustrate this point, the following calculations are being done. Let us consider a case where the soil resistivity is 3000 ohm centimeter and the current required for cathodic protection is 1 microampere per centimeter square. Substituting these values in this equation, it turns out that the potential drop across 1 centimeter is 1.5 millivolt, right. And for a tank of 4 meter diameter, the voltage drop from the edge to the center turns out to be 300 millivolt, right. So, let us look at the criteria for cathodic protection. We all know that the minimum potential required for cathodic protection is minus 0.85 volt with respect to copper sulphate electrode, for example. Then if you have to have a potential of minus 0.85 at the center, the edge of the tank should measure a potential of minus 1.1 volt with respect to saturated copper sulfate electrode. So, it is possible to calculate the potential of the tank at the center with respect to soil if we know the resistivity of the soil and the current density that required for cathodic protection. The other important requirement for the cathodic protection of the tanks are the ground bed. The resistance offered by the ground bed can be calculated as per the equation that we saw before. That is, in one of the lectures we talk about the anode ground bed resistance calculations, right. So, same can be used here to calculate the resistance offered by the ground bed. So, what we look at here is what is important is how the current is uniformly distributed in the tank. Okay. Sometimes you may have several tanks around actually. Okay. So, how the current is uniformly distributed, it depends upon the symmetry with which these anodes are distributed. We can also have a vertically drilled anodes can be distributed around the tanks actually in order that the current is uniformly distributed, or we can also have the angled anodes which gives you even better distribution of the current. Where we cannot have distributed anodes, we can also have deep well ground bed anodes installed for large storage tanks of let us say 300 meter diameter, the big tank, and we can have a deep well ground bed anodes. We know that the current distribution is much larger. It is easy to maintain remote anode, much easier with deep well ground bed anodes. The horizontal anodes are also kept where it is not possible to have deep well ground bed anodes, and for tanks with secondary containment linings it can be possible to do that. Okay. And deep grid patterns, the anodes of grid patterns are also used where double bottom cathodic protection layout are required, and only problem here is the current paths are constrained. So, the current distribution is very difficult. We talked about current distribution at the bottom of the tank. The current distribution at the ore of the tank also equally important. In this case, the other pipings need to be considered. You can have a remote anode, so that the current distribution becomes quite easier, or isolate the tank electrically for example. And in the first case you can have a remote anode wherein you can also talk about other pipings which are connected to the tank is done. We have seen the current distribution for the bottom of the tanks. The current distribution over the tank is also equally important. There are cases where the other pipings are considered, especially when the tanks are buried tanks, and where the pipings are part of the tanking process. You can have a single remote anode that will take care of completely the cathodic protection of the tanks and so on, or it is possible to isolate the tank electrically and confine the cathodic protection only to the tank. You can also have distributed sacrificial anodes, okay, and there are tank forms, there are multiple tanks are present, in which case you can have a distributed anodes even between the anodes. We can have the tanks we can have the anodes installed so that the current is evenly distributed. The whole idea here is the current distribution has to be uniform, and so the configuration of the anodes are accordingly done. Let us move on to the next topic, which is the cooling water system, wherein heat exchangers are used, and these heat exchangers are required to be cathodically protected. The main problem in the case of cooling water system is the cooling water systems, the heat exchangers, they use bimetallics, and tubes are mainly consisted of stainless steels, titanium alloys and copper alloys, where the shell and the tube sheets are made up of steels, and therefore, the galvanic corrosion occurs. In order to prevent the galvanic corrosion, the cathode protection is done, and the cathode protection is generally done in the water boxes, and the protection will extend into the tubes to the extent of about 8 times the tube diameter. So, the galvanic corrosion in that location is significantly reduced because of the cathode protection that is offered for the water boxes. The water boxes are generally coated, and for fresh water the current required for cathode protection lies in the range of 10 to 30 milliampere per centimeter square, and zinc anodes are generally used. However, if the temperature is higher, goes beyond 80 degrees Celsius, and zinc anodes cannot be used, and magnesium needs to be used in this case. But if magnesium is used, it corrodes very high and offers over protection, needing a resistor to control the current delivered for protection of the structures. Whereas in the case of aluminum, whereas in the case of seawater, the aluminum alloys are used. The heat exchangers sometimes use the impressed current cathodic protection system as well, but however, it is better to use sacrificial anode systems because it makes it more easier to maintain. Let us look at the offshore structures. The offshore structures that we discussed today are pipelines, pilings, jetties and floating structures. Okay. And the marine cathodic protection, as you put all of them, the general considerations are: you have a cathodic protection criteria which is minus 0.8 volts with respect to silver chloride electrode. Because the marine environment is more of chlorides, the saturated copper sulfate electrode is seldom used, rather they use silver chloride electrode, and so the potential against it is minus 0.8 volts. That is the criteria for cathode protection. You can also use 300 millivolt criteria because the electrolyte is highly conducting. So, the IR drop in the electrolyte is not very high. However, this does not take into consideration the resistance offered within the metallic structures. Use of zinc reference electrode is very common because zinc is less polarized anodically, and so the potential does not change when it is used as a reference electrode. No magnesium anodes are used because it will overprotect the structures. What is important is wherever you use high strength steels in the marine applications, since they are prone to hydrogen embrittlement, low driving force sacrificial anodes required to be used. One such anode is aluminum manganese anodes. Zinc anodes are better in brackish water as the aluminum passivates. For aluminum to act as a sacrificial anodes, it is possible to have chlorides. When the chlorides are less, the aluminum anodes passivate. The marine structures, both ICCP and sacrificial anodes are used, systems are used. If there are ICCP is used, we have iron silicon, the precious metal such as platinum is used, or titanium insoluble anodes, or even polymer anodes are used where you have concrete structures. ICCP is less capital than sacrificial anode cathode protection system for seawater applications because you need to have large amount of sacrificial anodes installed, and for a brackish water ICCP works better than the sacrificial anode systems. When you are going to use the sacrificial anodes, or when you are going to use impressed current anode systems, much the same way you do for soils, it is necessary to consider the anode resistance, the resistance offered by the anodes required to be seen, and these are the formula that are being used. They are, if you notice, they are significantly different from what was used for calculating resistance of anode beds in the soil. Okay. And if you are going to use bracelet anodes, we talk about the diameter of the bracelet anode and the width of the bracelet anodes are used. You can see that the equation to calculate resistance of the anode is changing depending upon this nature of the surface, flat surface, and the curved surface with the bracelet anodes. Okay. And very simplified equations are many times used. This is called a McCoy equation. It does not take into consideration the anode geometry. So, it is a very simple equations used to calculate the resistance offered by a given anode. All you need is the resistivity of the electrolyte, in this case the seawater maybe, and the area of the anode are used to calculate resistance offered by the anode. Let us look at the offshore structures now in specific. Let us take the pipelines. The pipelines are coated with the anti-fouling coatings. The offshore structures, a lot of marine growths, and in order to avoid the marine growths, anti-fouling coatings are given. And this one thing very important when you talk about pipelines is these pipelines are connected with the tankers for loading the products, maybe crude or something like that actually, okay, or discharging to the tanks. It can happen both the ways. And if ICCP is to be operated in this case, the ICCP is installed in the shore, and that works better actually. Okay. And for deep shore pipelines, the pipelines are well coated, because more you take care of coatings, less current is required for the cathode protection systems. The anodes again in this case are attached to the pipes, which are generally as bracelet anodes. This also reduces the buoyancy of the pipeline because adds to the weight of the pipeline, or it is also laid in the seabed, on the seabed, mounted on sledge or floating anodes. The sacrificial anodes are added whenever the pipeline terminates in a single structure, such as single point moorings. Care needs to be taken to avoid current entering the tankers that could introduce stray current corrosion of the structures. The offshore structures, we also have piling and jetties. Over here also you go for good coatings, poor coatings is a cause of concern. One of the problems in the piling and jetties is that when you have flash and tidal zones, the coating deteriorates because of continuous flashing of seawater actually. Okay. And again, if you have structures on the offshore and the onshores connected, the one in the seaside requires more current than on the land sides, okay, and need to be made electrically continuous. Suppose you are protecting cathodically from the onshore, then the structure to be electrically shorted in order that current flows. If you have structures in the offshores, the anodes need to be kept at different levels so that the current is uniformly distributed in the structures. Okay. That is, anode distribution is very important for even distribution of current and so even protection of the structures. There are some corrosion occurring in the structures. The resistance, the structure can offer significant resistance for the flow of current, and so unlike the pipelines that are normally buried in the ground, the cathode lead requires to be distributed so that the ohmic drop within the leads are reduced and so that the current is better distributed. Sizing of the anodes are very important when you talk about use of the sacrificial anodes. The anode weight, what is the weight required for cathode protection is calculated based on these equations. W upon C should be greater than I by L, where W means the anode weight, the current consumption, rate for given structures given in terms of kg per ampere year, okay, and the current required to protect the structures and the life of these structures. That decides what should be the anode size in terms of the weight. The anode size selection also depends upon the current that is required. There should be adequate driving voltage. We have seen this during the cathode protection of pipelines, where the anode ground bed resistance were calculated. That is very much applicable over here also. That is, the current that is required, okay, would be depending upon the resistance of the electrolyte, and so the driving force. The driving force of a given anode is known, and so it is necessary that R should be adjusted. How to adjust R we have seen earlier, right? There is a relation between R and the area of the anode. So, it is possible that if the area of the anode becomes smaller, you will not get sufficient current to protect the structures, or the driving voltage is going to be reduced. So, the sizing of the anode is based on the weight required to protect for the given life, as well as the driving force that is required to drive the required current for the structures. Let us come to the last topic of today's lecture. We talk about the ships. So, again we are not going into details about the cathode protection that is applied to ships, but what we look at here is the general concepts, overall approaches for the cathode protection of ships. As we are all aware that coatings are applied onto the ships, but however there are certain areas of the ships where the coatings get damaged very readily, and so the current requirement for protecting the ship would depend upon damaged area of the ship hull. So, the damaged area is used to compute the current requirement for protecting the ships. The anodes are concentrated more on the bow, on the stern side, where the coating is damaged. As we have seen before, that when the coating is damaged, the current requirement becomes more, and so the anodes are more concentrated on these locations where the coating is likely to get damaged in service. It is also that the stern is also the location where the galvanic couples between the propeller and the hulls are possible. So, in order to reduce the galvanic corrosion between these two, the propeller is made up of relatively noble metal, as compared to the hull, and so the hull will suffer corrosion. So, in order to control that, more galvanic anodes are located in these locations. The current distribution is very important, and so small anodes are distributed so that so that the current is uniformly. The one more problem that happens at the above location is that there is a drag associated with the anodes. So, if the larger the anode, more will be the drag, and so small anodes are distributed in order to reduce the drag onto the ships. The ship size are becoming larger. Using simply the sacrificial anode, cathodic protection system is unviable, and so the ICCP is used. In fact, ICCP and cathodic protections are used together in most of the ships. The one problem with the ICCP is that it can cause paint disbonding, it can cause hydrogen embeddlement of cast hardened shafts, bowls and other high strength attachments to the steels. One of the problems in using ICCP for the ship hull is that these anodes are mounted on the ship hull. So, this should be electrically isolated, otherwise the ship hulls will become effective anodes for passing current, and so they will suffer huge corrosion. So, in order to give in order to separate the impressed current anodes, the dielectric seals are used. These dielectric seals generally are glass reinforced epoxies, and that separates the anode on the ship hulls. And it is also known that the propeller is to be grounded, otherwise the current will stray from the propeller into the ship, leading to the stray current corrosion of occurring on the impeller hub bosses. So, propellers need to be grounded in order to avoid stray current corrosion in the ships. So, we have come to the end of this lectures. Before I close this lecture, I would like to summarize what you have seen today. Cathodic protection of tanks, offshore structures, ships is what we saw today, and we also saw that in the terms of structures, in terms of the tanks, the corrosion behavior of the tanks exposed to soil are very much similar to the pipelines which are buried in the soil. And the corrosion issues, uniform distribution of cathodic protection current is the key for effective protection of tanks against corrosion. And one issue that is very specific to the tanks is measuring the soil potential at the center of the tank is a problematic one. We also seen how to work on the problem. Either we use perforated plastic conduits through which the reference electrodes are sent, or it is possible to calculate the potential of the tank at the center if you know the resistivity of the soil and the current density required for cathodic protection and the measured value of the tank to soil potential at the edge. The offshore structure environment as opposed to the soil is quite uniform, and required current is significantly higher, and it can also vary significantly, because if there is a tidal or if the ship moves, for example, the current requirement becomes larger. Mounting ICCP anodes on the ship is another problem, because if the dielectric shield breaks down, then the ship hull can suffer severe corrosion.